Look up at the night sky on a cold winter evening, and you will see something that has captured human imagination for thousands of years. There, stretching across the darkness like a cosmic giant frozen in time, stands the constellation Orion, the hunter. You see 3 bright stars forming his belt, glowing like jewels strung on an invisible thread. You see his shoulders marked by brilliant beacons of light, his feet planted firmly against the river of stars we call the Milky Way, his sword hanging from his belt, and his arm raised high as if ready to strike at some invisible prey. Ancient civilizations saw this pattern and told stories of gods and heroes, warriors and hunters, legends that would echo through millennia. The Egyptians saw Osiris, god of the afterlife. The Greeks saw a mighty hunter boasting he could kill any creature on earth. Indigenous peoples across every continent looked up and recognized patterns that spoke to their own cultures and myths. But here is the truth that would have shattered the understanding of every ancient astronomer and storyteller who ever gazed upon these stars. Orion is not what it appears to be. Those stars that seem to form a neat pattern, close together like drawings on a canvas, are actually scattered across incomprehensible distances, separated by light years so vast that calling them neighbors is like calling 2 cities on opposite sides of the Earth neighbors. Some of these stars are relatively close, while others are so distant that their light has been traveling toward us for longer than human civilization has existed. The size of Orion, the true scale of this celestial hunter, is so enormous that it defies human comprehension and challenges everything we think we understand about distance, space, and our place in the cosmos. This is not just a story about measuring stars. This is a journey into understanding how human beings learned to reach across the universe with nothing but mathematics and observation to grasp truths about scales that dwarf anything in our earthly experience. Introduction to the Celestial Hunter. When we look at constellations in the night sky, we are seeing what astronomers call asterisms, patterns of stars that appear to be grouped together from our perspective on Earth, but may have no actual physical connection to one another. Orion is perhaps the most recognizable and beloved of all constellations, visible from almost every inhabited place on our planet at some point during the year. It dominates the winter sky in the northern hemisphere and the summer sky in the southern hemisphere, rising in the east and marching westward through the night as Earth rotates beneath the stars. The constellation is outlined by 7 major bright stars that form a distinctive hourglass or bow tie shape, with 3 stars in a straight line marking the belt at the center. Above the belt, 2 bright stars mark the shoulders of the hunter. Below the belt, 2 more bright stars mark his knees or feet. Hanging from the belt is a vertical line of fainter stars forming the sword, and extending from one shoulder is a curved line suggesting a raised arm holding a club or shield. This pattern is so distinctive that once you learn to recognize it, you will never mistake it for anything else in the heavens. To understand how big Orion really is, we must first understand what we mean by size when discussing constellations. Unlike planets or stars, which are physical objects with measurable dimensions, constellations are human constructs, patterns we impose on the random distribution of stars across the sky. The stars that form Orion are not bound together by gravity, not orbiting each other, not part of any coherent physical system. They simply happen to lie in roughly the same direction as seen from Earth, creating an illusion of connection where none truly exists. So when we ask how big Orion is, we are really asking several related questions. How much area does the constellation cover in our sky? How far away are the individual stars that compose it? What is the 3-dimensional volume of space that contains these stars? How do the distances between these stars compare to the distance from Earth to them? These questions have answers that will take us on a journey through the history of astronomy, the nature of stars, the structure of our galaxy, and the methods by which humanity learned to measure the unmeasurable. The constellation Orion covers a substantial area of the night sky, officially occupying 594 square degrees out of the 41,253 square degrees that cover the entire celestial sphere surrounding Earth. This makes Orion the 26th largest constellation out of the 88 officially recognized constellations defined by the International Astronomical Union. To put this in perspective, imagine the night sky as the inside of a giant dome surrounding Earth. If you divided this dome into 41,253 equal squares, Orion would occupy about 594 of them, roughly 1.4% of the entire sky. The constellation stretches about 20 degrees from top to bottom and about 15 degrees from side to side, meaning if you held your fist at arm's length against the sky, Orion would span roughly 2 fist widths vertically and 1.5 fist widths horizontally. This apparent size has nothing to do with the actual physical distances involved, but simply reflects how much of our sky the constellation pattern occupies from our earthly viewpoint. But apparent size in the sky tells us almost nothing about the real scale of what we are observing. The 7 major stars of Orion range in distance from approximately 243 light-years for the star Bellatrix to about 2,400 light-years for the star Alnilam, one of the belt stars. A light-year is the distance light travels in 1 year, moving at its constant speed of about 186,000 miles per second, or 300,000 kilometers per second. In 1 year, light covers about 6 trillion miles, or roughly 9.5 trillion kilometers. The nearest star in Orion is therefore about 1.5 quadrillion miles away, while the farthest is roughly 14 quadrillion miles distant. The difference between the nearest and farthest stars of Orion is approximately 2,000 light-years, meaning these stars that appear to be neighbors in our sky are actually separated by a gulf of space measuring 12 quadrillion miles. To put this in context, if you could travel at the speed of the fastest spacecraft ever built, which would take you from Earth to the Moon in just a few hours, it would take you more than 6 million years to cross the distance between the nearest and farthest stars of Orion. Understanding these distances requires us to abandon any intuitive sense of scale and embrace the reality that space is almost entirely empty, with tiny islands of matter separated by vast oceans of nothing. The stars we see as the constellation Orion are scattered through a volume of space that is roughly cylindrical in shape, with Earth near one end looking through this cylinder toward the depths of our galaxy. The cylinder is about 2,000 light-years deep and perhaps 20 to 30 light-years across in the directions perpendicular to our line of sight, though calculating the cross-sectional dimensions requires careful analysis of each star's position in 3 dimensions. This volume contains not just the 7 bright stars we recognize as forming the constellation pattern, but also hundreds of fainter stars visible through telescopes, clouds of gas and dust where new stars are forming, the remnants of dead stars, and vast regions of empty space between these scattered objects. Orion is not a thing, but a direction, a window through which we look into a particular region of our galaxy that happens to contain several very bright, very luminous stars that dominate our view and create the familiar pattern we have named and mythologized, the ancient recognition. The story of Orion begins not with telescopes or scientific measurement, but with naked-eye observation by people who lived thousands of years before the invention of writing. Archaeological evidence suggests that humans have recognized and named the Orion constellation for at least 5,000 years and possibly much longer. Ancient stone monuments, including prehistoric structures that predate the pyramids, appear to be aligned with the stars of Orion's belt, suggesting that these stars held significance for cultures that left no written records. The oldest written references to Orion appear in texts from ancient Mesopotamia, Egypt, and China, dating back 3,000 to 4,000 years. These civilizations gave the constellation different names and associated it with different myths, but all recognized the same basic pattern in the sky, demonstrating that the human ability to see patterns and create meaning from random arrangements is universal across cultures and time. The ancient Egyptians had a particularly deep connection to Orion, which they called Sa, and associated with Osiris, the god of death, resurrection, and the afterlife. Egyptian mythology held that Osiris was murdered by his brother Set, cut into pieces, and scattered across Egypt. His wife Isis gathered the pieces and resurrected him long enough to conceive their son Horus before Osiris descended to rule the underworld. The Egyptians saw Osiris in the stars of Orion, which appeared in the pre-dawn sky during the season when the Nile flooded, bringing life-giving water and nutrients to the farmlands along the river. This timing associated Orion with fertility, rebirth, and the cycle of life, death, and renewal. The three pyramids of Giza, built around 4,500 years ago, are famously aligned with the three stars of Orion's belt, though the exact nature and intention of this alignment remains debated among archaeologists. What is certain is that the ancient Egyptians watched Orion carefully, tracked its movements through the year, and embedded its pattern into their architecture and religious practices. The ancient Greeks developed an elaborate mythology around Orion, creating multiple contradictory stories that nevertheless shared common elements. In the most popular version, Orion was a giant hunter of extraordinary size and strength, the son of Poseidon, god of the sea. Orion boasted that he could hunt and kill every animal on Earth, which angered Gaia, the Earth goddess, who sent a giant scorpion to kill him. The scorpion stung Orion and killed him, and both the hunter and the scorpion were placed in the sky as constellations, positioned so that as Scorpius rises in the east, Orion sets in the west, creating the illusion that the hunter eternally flees from the creature that killed him. Other versions of the myth involve Orion's romantic pursuits, his blinding and subsequent healing, and various conflicts with gods and goddesses. What all these stories share is the characterization of Orion as a figure of tremendous power, pride, and tragedy, a hero brought low by his own hubris. The Greeks also recognized specific stars within the constellation, naming them individually and creating additional myths around them. Ancient Chinese astronomers incorporated Orion into their own system of constellations, which divided the sky differently from the Greek tradition that eventually gave us our modern constellation boundaries. In Chinese astronomy, the stars of Orion's belt and sword formed a constellation called Shen, one of the 28 lunar mansions that marked the moon's path across the sky. Shen represented a powerful warrior or general and was associated with military matters and the autumn season. Chinese astronomers kept detailed records of observations over thousands of years, noting the positions of planets as they moved through Orion, recording the appearance of comets and new stars, and tracking subtle changes in stellar positions. These records, preserved in historical texts, provide modern astronomers with valuable data about celestial events that occurred before the invention of telescopes. The Chinese tradition of careful astronomical observation contributed significantly to humanity's gradual understanding of how the sky changes over time and how celestial objects move according to regular, predictable patterns. Indigenous peoples across the Americas, Australia, Africa, and the Pacific Islands also recognized patterns in the region of sky we call Orion, though their constellation patterns and mythologies differed from the Greco-Roman tradition. Many Native American cultures saw the three belt stars as representing different things in different tribes, sometimes as three hunters or warriors, sometimes as animals, sometimes as supernatural beings. Australian Aboriginal peoples, viewing the sky from the southern hemisphere where Orion appears inverted compared to northern views, incorporated the constellation into complex dreamtime stories that explained creation, law, and the relationships between people, land, and cosmos. These diverse cultural interpretations of the same stars remind us that constellations are human creations, meaningful patterns imposed on random arrangements, reflecting the needs, values, and imagination of the people who named them. There is no objective reality to Orion as a hunter or to Scorpius as a scorpion. These are stories we tell, ways of organizing the overwhelming complexity of thousands of visible stars into memorable, meaningful patterns. The breakthrough of distance. For thousands of years, humans looked at Orion and had no idea how far away the stars were or whether they were all at the same distance. The ancient Greeks and medieval European astronomers believed that all stars were fixed to a celestial sphere at the same distance from Earth, like lights mounted on the inside of a giant dome. This model seemed to explain the observations perfectly well. The stars maintained their relative positions night after night, year after year, century after century, suggesting they were all attached to a single rotating sphere. The lack of any observable parallax, the apparent shift in position when viewed from different locations, suggested the stars were so far away that any parallax would be undetectable, or that they truly were all at the same distance on a celestial sphere. It was not until the development of better telescopes and more precise measuring instruments in the 18th and 19th centuries that astronomers could finally begin measuring stellar distances and discovering the three-dimensional structure of the universe. The breakthrough came with the measurement of stellar parallax, which works on the same principle as human depth perception. Your two eyes see the world from slightly different angles, and your brain combines these two views to calculate distances to objects. The closer an object, the more different it appears between your left and right eye views. If you close one eye and hold up your finger, then switch eyes, your finger appears to jump position against the background. Stars are so far away that the distance between your two eyes creates no detectable parallax, but the distance from one side of Earth's orbit to the other, about 186 million miles, is large enough to create tiny but measurable parallax shifts for the nearest stars. Imagine Earth's orbit as a giant baseline. Observe a star in January when Earth is on one side of the Sun, then observe it again in July when Earth is on the opposite side of the Sun, and measure how much the star appears to shift position against more distant background stars. The amount of shift is inversely proportional to the star's distance, with larger shifts indicating nearer stars and smaller shifts indicating more distant stars. The first successful measurement of stellar parallax was achieved in 1838 by the German astronomer Friedrich Bessel, who measured the parallax of a star called 61 Cygni and calculated its distance at about 11 light-years, roughly 64 trillion miles. This measurement proved that stars were other suns at enormous distances, separated by gulfs of space vastly larger than anything in the solar system. Other astronomers quickly followed with parallax measurements of additional stars, gradually mapping the three-dimensional structure of our stellar neighborhood. The stars of Orion, however, presented challenges. Most of them are so distant that their parallax angles are extremely small, requiring decades of patient observation with increasingly sophisticated instruments before accurate distances could be determined. Early measurements had large uncertainties and sometimes gave contradictory results, leading to scientific debates about which stars were truly near and which were far. One of the first Orion stars to have its distance measured was Rigel, the bright blue-white star, marking the hunter's left foot or knee depending on how you visualize the constellation pattern. Early measurements suggested Rigel might be several hundred light-years away, but the star was so bright that it had to be intrinsically very luminous to appear so brilliant from such a distance. As measurement techniques improved through the 20th century, astronomers refined the distance to Rigel, eventually settling on a value of approximately 864 light-years, though some uncertainty remains because Rigel is actually a multiple star system with several components that complicate the measurements. The star Betelgeuse, the famous red supergiant marking Orion's right shoulder, proved even more challenging to measure because its enormous size and variable brightness make it difficult to pinpoint its exact center, and because the star is surrounded by an extended atmosphere and shells of material expelled from its surface. Modern measurements place Betelgeuse at roughly 550 light-years, though estimates range from 500 to 700 light-years depending on the method used. The three stars of Orion's belt, Alnitak, Alnilam, and Mintaka, are among the most distant of the major constellation stars, all lying between approximately 800 and 1200 light-years from Earth. These measurements came relatively late in the history of astronomy because the stars are so far away that their parallax angles are less than 5/1000ths of an arcsecond, angles so small that they correspond to the width of a human hair viewed from a distance of about 8 miles. Measuring such tiny angles requires space-based telescopes free from the blurring effects of Earth's atmosphere, or decades of careful ground-based observations that average out atmospheric distortions. The European Space Agency's Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars with unprecedented precision, and its successor Gaia, launched in 2013, has measured positions and distances for more than 1 billion stars, providing the most accurate three-dimensional map of our galaxy ever created. These missions finally gave us reliable distances to all the major stars of Orion, revealing the true scale of the constellation. The Belt Stars. The three stars of Orion's belt form one of the most recognizable patterns in the entire night sky. A perfectly straight line of three roughly equally bright stars stretching across about 3 degrees of sky, roughly 6 times the apparent diameter of the full moon. From our perspective on Earth, these stars appear so similar in brightness and position that it seems natural to assume they are related, perhaps a group of stars born together or orbiting each other. The reality is far more complex. While the belt stars do share some connections, they are not a simple triple star system, but rather 3 individual massive stars at different distances, each with its own history and fate. From east to west, the belt consists of Alnitak, Alnilam, and Mintaka, Arabic names meaning the girdle, the string of pearls, and the belt, respectively. These names date back over 1,000 years to when Arab astronomers were the world leaders in observational astronomy and gave Arabic names to many of the brightest stars, names we still use today. Alnitak, the easternmost star of the belt as seen from Earth, lies approximately 815 light-years away, making it the nearest of the 3 belt stars, though still almost 5 trillion miles distant. Alnitak is actually a triple star system, consisting of 3 massive hot blue stars orbiting their common center of gravity. The primary star, Alnitak A, is a blue supergiant with a mass about 33 times the Sun's mass and a luminosity approximately 120,000 times the Sun's luminosity. This means Alnitak A emits as much energy in just 7 hours as the Sun emits in an entire year. The star's surface temperature is approximately 29,000 degrees Celsius, nearly 5 times hotter than the Sun's surface, giving it an intense blue-white color. At this temperature, the star emits most of its energy in the ultraviolet part of the spectrum, invisible to human eyes, and what we see as visible light is just a small fraction of the star's total energy output. Alnitak A has a companion star, Alnitak B, orbiting at a distance that varies over a period of about 1,500 days. Alnitak B is itself a massive blue star with about 28 solar masses and 66,000 solar luminosities, making it extraordinarily luminous by any standard except in comparison to its even brighter companion. The system also includes a third star, Alnitak C, orbiting at a much greater distance. Alnilam, the central star of the belt, is the most distant and most luminous of the three, lying approximately 2,400 light-years from Earth. This makes Alnilam about 3 times as distant as Alnitak, yet it appears roughly the same brightness in our sky because it is intrinsically much more luminous. Alnilam is a blue supergiant with a mass estimated at 64 times the Sun's mass and a luminosity approximately 832,000 times the Sun's luminosity, making it one of the most intrinsically bright stars visible to the naked eye. If Alnilam were placed at the same distance as Sirius, the brightest star in our night sky, at only 8.6 light-years away, Alnilam would appear brighter than the full moon and would be visible in broad daylight, casting distinct shadows at night. The star's tremendous luminosity comes from its enormous size and extremely high surface temperature of about 27,500 degrees Celsius. Alnilam has expanded to a radius about 42 times the Sun's radius, making it large enough that if placed at the center of our solar system, its surface would extend nearly to the orbit of Mercury. The star is also losing mass through a powerful stellar wind, expelling material at speeds of thousands of kilometers per second and losing roughly 1/1,000,000th of its mass every year. Mintaka, the westernmost star of the belt, lies approximately 915 light-years from Earth, making it intermediate in distance between Alnitak and Alnilam. Like Alnitak, Mintaka is a multiple star system containing several massive hot stars. The primary component, Mintaka A, is a blue giant star with about 24 solar masses and 90,000 solar luminosities. Mintaka A has a close companion star that orbits every 5.7 days, so close that the two stars are nearly touching, and tidal forces have distorted their shapes into ellipsoids rather than spheres. This close binary system is what astronomers call an eclipsing binary, because from our viewing angle, the two stars pass in front of each other during their orbit, causing the combined brightness to decrease periodically. The brightness dips are small, only about 20%, but they occur with clockwork regularity and provided early evidence that Mintaka was not a single star, but a system of multiple stars. The system also includes additional, more distant stellar companions, making Mintaka a complex multiple star system like Alnitak. All 3 belt stars are therefore not simple single stars, but gravitationally bound systems of multiple massive stars, adding even more richness to the already complex structure of the Orion constellation. The 3 belt stars, despite being at different distances ranging from about 800 to 2,400 light-years, are nevertheless physically associated in an important way. All 3 stars are members of what astronomers call the Orion OB1 Association, a large, loose grouping of hot, massive stars that formed from the same giant cloud of gas and dust between about 8 and 12 million years ago. Star formation does not create isolated individual stars, but rather clusters and associations of stars born together from gravitationally collapsing regions of interstellar gas. The Orion OB1 Association contains hundreds of hot blue stars of spectral types O and B, the most massive and luminous star types, spread across a region of space several hundred light-years across. The association is not gravitationally bound like a star cluster where stars orbit each other indefinitely, but rather a loose group of stars that share common motion through space, all moving in roughly the same direction at roughly the same speed because they were born from the same parent cloud and inherited its overall motion. Over tens of millions of years, the individual stars will drift apart as their slightly different velocities cause them to gradually separate, eventually destroying the association and scattering its member stars throughout the galaxy. The 3 belt stars are currently separated by over 1,000 light-years along our line of sight, but they are connected by their common origin and similar ages, making them siblings separated by vast distances but still part of the same stellar family. The shoulder stars. The shoulders of Orion are marked by two of the constellation's brightest and most famous stars, Betelgeuse and Bellatrix, which could hardly be more different from each other despite appearing as a matched pair to the casual observer. Betelgeuse marks the eastern or left shoulder as we see the constellation from Earth, glowing with a distinctive orange-red color that stands out dramatically against the blue-white stars that dominate the rest of Orion. The name Betelgeuse derives from Arabic, though its exact etymology is uncertain and possibly corrupted through centuries of translation errors. The star has captured human imagination for millennia because of its color, brightness, and intriguing variability. Betelgeuse is a red supergiant, one of the largest known stars in our galaxy, with a radius that varies but averages roughly 700 times the Sun's radius. If placed at the center of our solar system, Betelgeuse would extend beyond the orbit of Mars and possibly reach the asteroid belt, swallowing Mercury, Venus, Earth, and Mars. The star's enormous size, combined with a relatively cool surface temperature of about 3,500 degrees Celsius, gives it a luminosity approximately 126,000 times the Sun's luminosity, though this value is uncertain and varies as the star pulsates. Betelgeuse lies approximately 550 light-years from Earth, making it one of the nearer major stars in Orion, though still over 3 trillion miles distant. The star is classified as a semi-regular variable, meaning its brightness changes over time in a roughly periodic pattern, but with significant irregularities. The brightness varies by about 1 magnitude, enough that keen-eyed observers can notice the changes over months or years. The variation occurs because the star is pulsating, expanding and contracting as waves of pressure and energy ripple through its enormous interior. When the star expands, it cools and dims slightly. When it contracts, it heats and brightens. These pulsations are not regular like a clock, but show complex patterns with multiple overlapping periods, ranging from about 400 days to around 6 years. In late 2019 and early 2020, Betelgeuse underwent an unusual and dramatic dimming event, where its brightness dropped to roughly 40% of normal, sparking intense interest and speculation that the star might be about to explode as a supernova. Subsequent research revealed that the dimming was caused by a massive ejection of material from the star's surface that condensed into a cloud of dust, temporarily blocking some of the star's light from reaching Earth. The star has since returned to normal brightness, but the event reminded astronomers that Betelgeuse is an unstable giant nearing the end of its life. Bellatrix marks the western or right shoulder of Orion, glowing with a blue-white color, typical of hot, massive stars. The name Bellatrix comes from Latin meaning female warrior, one of the few major stars to have a Latin rather than Arabic name. Bellatrix lies approximately 243 light-years from Earth, making it the nearest of the 7 major Orion stars, though still roughly 1.5 trillion miles distant. Despite being closer than Betelgeuse, Bellatrix appears slightly fainter in our sky because it is intrinsically less luminous than the red supergiant. Bellatrix is a blue giant star with a mass about 8.6 times the Sun's mass and a luminosity approximately 9,500 times the Sun's luminosity, making it extraordinarily luminous by any standard, except in comparison to the even brighter supergiants elsewhere in Orion. The star's surface temperature is approximately 22,000 degrees Celsius, giving it an intense blue-white color and causing it to emit most of its energy in the ultraviolet part of the spectrum. Bellatrix is rotating rapidly, spinning on its axis with an equatorial velocity of about 250 kilometers per second, fast enough that the star is noticeably flattened at the poles due to centrifugal force. The contrast between Betelgeuse and Bellatrix illustrates the diversity of stars that can appear similar in brightness from Earth, despite being dramatically different in nature. Betelgeuse is an evolved red supergiant nearing the end of its life, having already exhausted the hydrogen fuel in its core and now fusing heavier elements in shell-burning phases that will ultimately lead to a supernova explosion. The star is cool, enormous, and losing mass through a powerful stellar wind that carries away approximately one solar mass every 100,000 years. Bellatrix, by contrast, is a main sequence or early giant star still fusing hydrogen in its core, hot, compact, and stable, with millions of years remaining before it exhausts its core hydrogen and begins evolving toward the supergiant phase. Eventually, Bellatrix will also expand into a red giant or supergiant and possibly explode as a supernova, but that fate lies far in its future, while Betelgeuse's supernova could occur at any time from tomorrow to 100,000 years from now. Despite their different natures and evolutionary states, both stars appear as bright points of light marking the shoulders of the hunter, demonstrating again how misleading appearances can be in astronomy. The distance between Betelgeuse and Bellatrix is substantial, even though they appear close together in our sky. Bellatrix at 243 light-years and Betelgeuse at 550 light-years are separated by about 307 light-years along our line of sight, equivalent to roughly 1.8 quadrillion miles, or about 29,000 times the distance from Earth to Pluto. In directions perpendicular to our line of sight, they are separated by somewhat smaller distances calculated using trigonometry from their angular separation in the sky and their distances from Earth. But the exact perpendicular separation depends on the three-dimensional geometry and amounts to roughly 10 to 20 light-years. These two stars, which appear to be neighbors marking opposite shoulders of the same figure, are actually separated by distances so vast that light takes over 3 centuries to travel from one to the other. If an observer were stationed near Bellatrix and looked toward Betelgeuse, the red supergiant would appear as a bright red star in their sky, but it would not be part of the Orion constellation pattern because the pattern only exists from Earth's viewpoint. From any other location in the galaxy, the stars of Orion would be scattered randomly across the sky with no recognizable pattern, and entirely different chance alignments would form the constellations visible from that location, the knee and foot stars. The feet or knees of Orion are marked by 2 bright blue stars named Rigel and Siph, which form the southern corners of the constellation's quadrilateral pattern. Rigel is the 7th brightest star in the entire night sky and usually the brightest star in Orion, though Betelgeuse occasionally surpasses it during periods when the red supergiant's variable brightness peaks. The name Rigel derives from Arabic meaning foot, specifically the left foot of the giant as seen from Earth. Rigel lies approximately 864 light-years from Earth, making it roughly 3.5 times as distant as Betelgeuse, but appearing brighter because it is intrinsically more luminous. Rigel is a blue supergiant with a mass estimated at 21 times the Sun's mass and a luminosity approximately 120,000 times the Sun's luminosity, though some estimates place the luminosity even higher at 200,000 solar luminosities. The star's surface temperature is approximately 11,000 degrees Celsius, somewhat cooler than the blue supergiants of the belt, but still hot enough to give Rigel a brilliant blue-white color. The star has expanded to a radius about 78 times the Sun's radius, making it large enough that if placed at the center of our solar system, its surface would extend about 1/3 of the way from the Sun to Mercury's orbit. Rigel is actually a multiple star system containing at least 4 components, though the additional stars are so much fainter than the primary that they are difficult to observe except with large telescopes. Rigel B, the brightest companion, is itself a close binary pair of two stars orbiting each other, and these stars orbit the primary Rigel A at a projected separation of about 2,000 astronomical units, roughly 50 times the distance from the Sun to Pluto. At this distance, Rigel B takes tens of thousands of years to complete one orbit around Rigel A. There may be additional fainter companions as well, making Rigel a complex system of multiple stars bound together by gravity. The existence of these companions complicates measurements of Rigel's distance and luminosity because astronomers must account for the light contributed by the secondary stars, though Rigel A is so much brighter than the others that it dominates the system's appearance. The blue supergiant primary is in an unstable phase of evolution, having exhausted the hydrogen in its core and begun fusing hydrogen in a shell around the core while the helium core contracts. This shell burning causes the star to expand and brighten, and eventually Rigel will evolve into an even larger red supergiant like Betelgeuse before exploding as a supernova. Scythe, marking the opposite knee or foot, is considerably fainter than Rigel but still a prominent star and one of the brighter stars in the night sky overall. The name Scythe also derives from Arabic, though its meaning is less certain than that of Rigel. Scythe lies approximately 650 light-years from Earth, making it intermediate in distance among the major Orion stars. Like Rigel, Scythe is a blue supergiant, but less massive and luminous than its partner. Scythe has a mass about 15.5 times the Sun's mass and a luminosity approximately 57,000 times the Sun's luminosity, making it extremely luminous by any standard, except in comparison to the other supergiants in Orion. The star's surface temperature is approximately 26,000 degrees Celsius, considerably hotter than Rigel despite being less luminous overall, because Scythe is smaller, with a radius only about 22 times the Sun's radius. This makes Scythe a smaller, hotter, denser supergiant compared to the larger, cooler Rigel, illustrating how stars of similar mass can have different properties depending on their evolutionary state and internal structure. The distance between Rigel and Scythe is substantial, with Rigel at 864 light-years and Scythe at 650 light-years, placing them about 214 light-years apart along our line of sight, plus some additional separation in the perpendicular directions based on their angular separation in the sky. Together, the four corner stars of Orion, Betelgeuse, Bellatrix, Rigel, and Scythe, outline a quadrilateral that spans distances of hundreds of light-years in 3 dimensions. From Earth, these 4 stars appear to mark the corners of a roughly rectangular figure, with Betelgeuse and Bellatrix at the top and Rigel and Scythe at the bottom, and the belt stars cutting across the middle. But in 3 dimensions, the geometry is completely different. Bellatrix, at 243 light-years, is the nearest corner star. Betelgeuse, at 550 light-years, and Scythe, at 650 light-years, form a middle layer. Rigel, at 864 light-years, is the farthest corner star. The stars do not form a rectangle at all, but rather mark the corners of an irregular, 3-dimensional shape with no particular symmetry or significance, except as viewed from our specific location. The knee and foot stars of Orion are, like the belt and shoulder stars, members of the broader Orion OB1 association, the loose grouping of young, massive stars that formed from a common giant molecular cloud. Rigel and Scythe are somewhat older than the belt stars, having formed perhaps 8 to 10 million years ago, compared to the belt stars 4 to 8 million years, but they are still young by astronomical standards and share the common motion and spatial association that characterizes the group. All of these massive blue stars are destined for short, violent lives ending in supernova explosions. Stars like the Sun, with one solar mass, can shine stably for about 10 billion years, but stars with 10 to 30 solar masses burn through their nuclear fuel hundreds or thousands of times faster, and live only 10 to 30 million years before exploding. This means that all the major blue stars of Orion are doomed to die relatively soon in astronomical terms, within the next few million to perhaps 20 million years, depending on their exact masses and evolutionary states. When they explode, they will briefly shine with the combined luminosity of billions of suns, becoming visible across millions of light-years of space before fading away, leaving behind neutron stars or black holes as remnants. The Sword and Nebula. Hanging from Orion's belt is a vertical line of fainter stars and glowing patches of light that form the Sword of the Hunter, and at the center of the sword lies one of the most magnificent objects in the entire night sky, the Orion Nebula, also known by its catalog designation Messier 42 or M42. The Orion Nebula is a vast cloud of gas and dust located approximately 1,390 light-years from Earth, glowing with the light of newborn stars embedded within it. The nebula spans about 24 light-years across, making it enormous compared to the distances between individual stars in our stellar neighborhood, though tiny compared to the distances between the major stars of the Orion constellation. The nebula is visible to the naked eye as a fuzzy patch of light in the sword, distinctly different from the sharp points of light that stars present. Through binoculars or a small telescope, the nebula reveals intricate structure with swirling patterns of bright and dark regions, giving it an appearance somewhat like a bird or butterfly with outstretched wings. Photographs with long exposures and sensitive cameras reveal even more detail, showing the nebula glowing in shades of red, pink, green, and blue, colors that correspond to different gases excited by ultraviolet radiation from hot young stars. The Orion Nebula is actually just the visible portion of a much larger structure called the Orion Molecular Cloud Complex, a giant region of cold gas and dust spanning hundreds of light-years that extends across much of the Orion constellation. This molecular cloud is one of the most active regions of star formation in our local region of the galaxy, containing enough material to form thousands of stars and currently hosting hundreds of protostars, young stellar objects still in the process of accumulating mass from their surroundings. The visible Orion Nebula represents a blister on the near side of the molecular cloud, where hot young stars have cleared away much of the gas immediately surrounding them and ionized the remaining gas, causing it to glow. The ultraviolet radiation from these stars heats the gas to temperatures of about 10,000 degrees Celsius, causing electrons to be stripped from atoms, and when these electrons recombine with atoms, they emit light at specific wavelengths characteristic of the elements present. Hydrogen emits red light, oxygen emits green light, and nitrogen emits red light, creating the colorful appearance of the nebula. At the heart of the Orion Nebula lies a cluster of 4 hot young stars called the trapezium, because they form a trapezoid pattern when viewed through a telescope. These 4 stars are the primary source of the ultraviolet radiation that makes the nebula glow. The brightest member of the trapezium, designated Theta 1 Orionis C, is a massive blue star with about 40 times the Sun's mass and roughly 200,000 times the Sun's luminosity, making it one of the most luminous stars in this region of the galaxy. This star is only about 300,000 years old, an infant by astronomical standards, having just recently begun fusing hydrogen in its core and emerging from the cocoon of gas and dust within which it formed. The trapezium stars are surrounded by hundreds of fainter young stars, most less than 1 million years old, forming what astronomers call the Orion Nebula Cluster. Observations with infrared telescopes, which can peer through the dust that blocks visible light, reveal even more young stars still buried within the molecular cloud, some still accreting material from surrounding disks, some surrounded by the protoplanetary disks from which planets will form. The Orion Nebula serves as a nearby laboratory for studying star formation, allowing astronomers to observe processes that occur throughout the galaxy but are usually hidden at greater distances or obscured by dust. By studying the Orion Nebula in detail, with telescopes operating at wavelengths from radio waves through infrared, visible light, ultraviolet, and X-rays, astronomers have learned how giant molecular clouds collapse under their own gravity to form stars, how the most massive stars form and affect their surroundings with intense radiation and powerful stellar winds, how planetary systems form in disks of gas and dust around young stars, and how stellar feedback, the energy and momentum injected into the interstellar medium by young stars, can both trigger new star formation and prevent it by dispersing the raw materials. The Orion Nebula has been observed by every major telescope and space observatory, generating thousands of scientific papers and spectacular images that have appeared in textbooks, documentaries, and popular media, making it perhaps the most photographed and studied object beyond our solar system. The Sword of Orion contains other notable objects beyond the Orion Nebula. Just north of M42 lies a smaller nebula designated M43, or Demiron's Nebula, which is actually part of the same cloud, but appears separated by a dark lane of dust. Farther north lies the star catalog designation 42 Orionis and its surrounding nebulosity. South of the Orion Nebula lies NGC 1977, another emission nebula glowing with the light of embedded young stars. These nebulae are all part of the vast Orion molecular cloud complex, and all lie at roughly the same distance from Earth, around 1,300 to 1,400 light-years, making them the nearest major region of ongoing massive star formation to our solar system. The proximity of this star-forming region is one reason Orion is such a prominent constellation. Not only does the region contain many intrinsically luminous young massive stars, but these stars are closer than they would be in many other constellations, making them appear brighter and more prominent in our sky. The combination of youth, massive luminous stars, and relative proximity makes the Orion region one of the most important areas of sky for understanding stellar birth and evolution. The three-dimensional structure. Understanding the true size of the Orion constellation requires constructing a three-dimensional map showing where each major star is located in space relative to Earth and to the other stars. This task, which would have been impossible before the space age, is now feasible thanks to precise distance measurements from satellites like Hipparcos and Gaia. By combining each star's distance with its position in the sky, we can calculate its location in a three-dimensional coordinate system with Earth at the origin. Imagine a coordinate system where the x-axis points toward 0 degrees right ascension on the celestial equator, the y-axis points toward 90 degrees right ascension on the equator, and the z-axis points toward the north celestial pole. Each star's position can be specified by three coordinates representing distances along these three axes. When we plot the major stars of Orion in this three-dimensional space, a surprising structure emerges that looks nothing like the familiar two-dimensional pattern we see from Earth. Bellatrix, the nearest major Orion star at 243 light-years, occupies a position in the foreground relatively close to Earth compared to the other constellation stars. If we imagine looking at the constellation from the side, perpendicular to our line of sight from Earth, Bellatrix would appear separated from the other stars, closer to Earth, and not part of the main grouping. Betelgeuse at 550 light-years and Siph at 650 light-years occupy middle positions, roughly twice as distant as Bellatrix, but still closer than the belt stars. Alnitak at 815 light-years, Rigel at 864 light-years, and Mintaka at 915 light-years form a middle-distance grouping, while Alnilam at 2400 light-years lies in the deep background, roughly 3 times as distant as Alnitak and 10 times as distant as Bellatrix. The Orion Nebula, at 1,390 light-years, occupies a position intermediate between the belt stars and Alnilam. These distances create a three-dimensional structure that extends about 2,200 light-years in depth, roughly 13 quadrillion miles, from the nearest major star to the farthest. In directions perpendicular to our line of sight, the stars of Orion are also spread out over considerable distances, though the perpendicular separations are generally smaller than the separations along our line of sight. The angular separation between stars in the sky, combined with their distances from Earth, allows calculation of their perpendicular separations using basic trigonometry. For example, Betelgeuse and Bellatrix are separated by about 13 degrees in the sky. At Betelgeuse's distance of 550 light-years, each degree corresponds to about 9.6 light-years of perpendicular distance. So the 13-degree separation corresponds to about 125 light-years perpendicular separation. Combined with the 307 light-years separation along the line of sight, the true three-dimensional distance between Betelgeuse and Bellatrix is about 332 light-years, calculated using the Pythagorean theorem. Similar calculations for other star pairs reveal that the major stars of Orion are scattered through a volume of space that is roughly cylindrical, about 2,200 light-years deep, and perhaps 50 to 100 light-years across. Though defining the exact cross-sectional size is somewhat arbitrary, since the stars do not form any particular geometric shape. The volume of space occupied by the Orion constellation stars is enormous, though difficult to comprehend in human terms. If we approximate the volume as a cylinder 2,200 light-years long and 75 light-years in diameter, the volume would be roughly 10 million cubic light-years, where 1 cubic light-year is the volume of a cube with sides 1 light-year long. To put this in perspective, there are several thousand stars within 10 light-years of the Sun, meaning the Orion region with a volume 1 million times larger might contain several billion stars, though actual star density varies greatly with location, and most of those stars would be faint red dwarfs invisible to the naked eye. The 7 major bright stars of Orion that form the constellation pattern are exceptional objects, far more massive and luminous than typical stars, which is why they stand out so prominently despite their great distances. For every massive blue supergiant like those in Orion, there are thousands of sun-like stars and millions of red dwarf stars. But these ordinary stars are too faint to see across the hundreds or thousands of light-years that separate us from the Orion region, so they do not contribute to the constellation pattern visible to our eyes. The three-dimensional structure of Orion reveals that the constellation is not a physical grouping in the sense of a star cluster where all members form together and orbit each other, nor even an association in the strictest sense where all members share common motion and origin. Rather, Orion is primarily a chance alignment of several loosely associated groups of stars that happen to lie in roughly the same direction from Earth. The belt stars and several other blue supergiants are members of the Orion OB1 association and did form from a common molecular cloud, making them physically related despite their large spatial separations. Betelgeuse and Rigel may also be associated members of this group, though their greater distances and different evolutionary states make their membership less certain. Bellatrix, lying much closer to Earth, is probably not part of the Orion OB1 association, but simply happens to lie in the same direction, creating a chance alignment. The Orion Nebula and the young stars within it represent the most recent generation of star formation in the region, still deeply embedded in the molecular cloud from which they formed. Understanding this three-dimensional structure reveals Orion as a complex region with multiple overlapping populations of stars at different distances and different evolutionary stages, unified only by their appearance in our sky. The historical measurement challenge. The history of measuring the distances to Orion's stars is a story of technological innovation, patient observation, and gradual refinement of techniques over more than 2 centuries. When the first successful stellar parallax measurement was achieved in 1838, it immediately became clear that measuring distances to stars as remote as those in Orion would be extraordinarily difficult. The parallax angle for a star 1,000 light-years away is about 3/1000ths of an arcsecond, where an arcsecond is 1/3600th of a degree. To visualize how small this is, imagine trying to measure the width of a human hair from a distance of several miles, or trying to distinguish 2 fireflies separated by 1 inch from a distance of 100 miles. Ground-based telescopes before the space age were limited by atmospheric turbulence, which causes stars to twinkle and blur, making precise position measurements difficult. Typical measurement precision was about 50 to 100 thousandths of an arcsecond under good conditions, barely sufficient to detect the parallax of stars a few hundred light-years away, and completely inadequate for more distant stars. Early attempts to measure distances to Orion stars relied on indirect methods that compared the star's spectra and brightness to those of nearer stars with known distances. The method of spectroscopic parallax, despite its name, does not actually measure parallax, but rather infers distance from luminosity. By analyzing a star's spectrum in detail, astronomers can determine its temperature, surface gravity, and chemical composition, which together indicate what type of star it is and therefore how intrinsically luminous it should be. Comparing the star's intrinsic luminosity to its apparent brightness as seen from Earth allows calculation of distance using the inverse square law, which states that brightness decreases with the square of distance. This method works reasonably well for stars of well-understood types but has significant uncertainties, typically 20 to 30%, because stellar luminosity depends on many factors including mass, age, and chemical composition, and because interstellar dust absorbs and scatters light, making distant stars appear fainter than they would if space were perfectly transparent. For much of the 20th century, distance estimates for Orion stars relied on spectroscopic parallax and other indirect methods, leading to considerable uncertainty and debate. Different studies published different distance estimates, sometimes differing by factors of 2 or more, because different assumptions about the star's properties and different methods of accounting for interstellar extinction led to different results. The distance to Betelgeuse was particularly controversial because the star's enormous size, variable brightness, and complex atmosphere made it difficult to characterize. Estimates ranged from less than 400 light-years to more than 700 light-years, a huge range that created significant uncertainty about the star's true luminosity and size. Similarly, the belt star's great distances meant that early estimates were highly uncertain, with some studies suggesting they might be twice as distant as we now know them to be. These uncertainties mattered for understanding the star's physical properties and evolutionary states, because a star's luminosity scales with distance squared, so if the distance is wrong by a factor of 2, the estimated luminosity is wrong by a factor of 4. The situation improved dramatically with the launch of the Hipparcos satellite in 1989, the first space mission dedicated to measuring stellar positions and parallaxes. Hipparcos operated above Earth's atmosphere, eliminating the blurring effects of atmospheric turbulence and allowing measurements with precision about 10 times better than ground-based observations. Over its 4-year mission, Hipparcos measured parallaxes for more than 118,000 stars, providing the first reliable distances for many moderately distant stars, including some members of the Orion constellation. Hipparcos measured Bellatrix's distance at approximately 243 light-years, with an uncertainty of only about 3%, and it measured distances to several fainter Orion members with similar precision. However, even Hipparchus was not precise enough to measure reliable parallaxes for the most distant Orion stars, like Alnilam, whose tiny parallax angle was at the limit of the satellite's capabilities, so uncertainties for these distant stars remained large. The Gaia mission, launched in 2013, represented another quantum leap in precision, measuring stellar parallaxes with accuracies about 100 times better than Hipparchus for bright stars. Gaia has measured positions and parallaxes for more than 1 billion stars, creating the most detailed three-dimensional map of our galaxy ever produced. Gaia's measurements finally provided reliable distances for all the major stars of Orion, including the distant belt stars and the enigmatic Betelgeuse. The Gaia data confirmed many earlier estimates but also revealed some surprises. Betelgeuse turned out to be somewhat closer than many previous estimates suggested, at about 550 light-years rather than 600 or 700 light-years, which affected calculations of its size and luminosity. The belt star's distances were refined, showing that Alnilam is even more distant than previously thought, at about 2,400 light-years, making it even more intrinsically luminous than earlier estimates suggested. These improved distances allowed astronomers to construct accurate three-dimensional maps of the Orion region and better understand the relationships between the various stars and star-forming regions in this part of the galaxy. The Orion molecular cloud. To fully understand how big Orion is, we must expand our view beyond the individual bright stars that form the visible constellation pattern, and consider the vast clouds of gas and dust that permeate the region and connect the various stellar populations. The Orion Molecular Cloud Complex is one of the largest structures in our local region of the galaxy, spanning an area of sky about 10 by 15 degrees, roughly 20 to 30 times the apparent diameter of the full moon. This angular size, combined with the cloud's distance of approximately 1,300 to 1,600 light-years, means the complex extends about 200 to 300 light-years across, making it enormous compared to typical interstellar clouds. The complex contains a total mass estimated at several 100,000 times the mass of the Sun, most of it in the form of molecular hydrogen gas, with temperatures around 10 to 50 degrees above absolute zero, cold enough that most molecules, except hydrogen, remain frozen onto tiny dust grains. The Orion Molecular Cloud Complex consists of several distinct components with individual names. The Orion A cloud, which includes the famous Orion Nebula, is the southernmost and most active component, currently forming hundreds of stars, including many massive hot stars that make the nebula glow. The Orion B cloud lies to the east of Orion A and is somewhat less massive and less active, but still contains regions of ongoing star formation, including the famous Horsehead Nebula and the Flame Nebula, both visible in long-exposure photographs as dark columns and bright regions of glowing gas. North of these clouds lies a structure called the Orion C, or Lambda Orionis cloud, associated with a hot, massive star named Lambda Orionis that has cleared a bubble in the surrounding molecular cloud. All these components are part of the larger Orion Eridanus superbubble, a vast cavity in the interstellar medium created by multiple generations of massive stars whose stellar winds and supernova explosions have swept out the gas in a region several hundred light-years across, piling it up in a shell surrounding the evacuated interior. The Orion Molecular Cloud Complex is actively forming stars, with star formation proceeding in waves as each generation of massive stars affects the surrounding gas and triggers or suppresses the formation of the next generation. The process begins when a giant molecular cloud, initially roughly uniform in density and temperature, begins to contract under its own gravity. As the cloud contracts, it fragments into smaller pieces, each of which contracts further to form individual stars, or small groups of stars. The most massive stars form first because they contract and heat up fastest, reaching the temperatures needed for nuclear fusion before their lower mass siblings. Once these massive stars ignite, they begin pouring out intense ultraviolet radiation and driving powerful stellar winds that heat and compress the surrounding gas. This feedback can have contradictory effects. In some regions, the compression triggers new star formation by pushing gas to densities high enough to collapse under its own gravity. In other regions, the heating and pressure prevent star formation by providing enough thermal and turbulent support to resist gravitational collapse. Eventually, the most massive stars explode as supernovae, sending shock waves racing through the molecular cloud at speeds of thousands of kilometers per second, compressing some regions and dispersing others. The current structure of the Orion region reflects several generations of this process. The oldest generation of massive stars, which formed about 10 to 12 million years ago, have already exploded as supernovae, leaving behind the Orion Eridanus superbubble and triggering the formation of the next generation. The belt stars Alnitak and Mintaka, along with several other hot blue stars in the region, formed about 5 to 8 million years ago and represent an intermediate generation. These stars are now affecting the remaining molecular cloud with their radiation and winds, creating the visible nebulosity we see as emission nebulae and reflection nebulae throughout the region. The youngest generation, represented by the stars in the Orion Nebula, including the trapezium cluster, is less than 1 million years old, with many stars still in the process of forming or just beginning to emerge from their birth clouds. This youngest generation will continue forming for another few million years until the remaining molecular cloud is either consumed by star formation or dispersed by stellar feedback, at which point star formation in the region will cease and the Orion molecular cloud complex will no longer exist as a coherent structure. The Orion molecular cloud complex is important not only for what it teaches us about star formation, but also for what it reveals about the structure and evolution of our galaxy. Molecular clouds are the raw material from which all stars form, and understanding how these clouds behave, how they fragment and collapse, how feedback affects them, and how they ultimately disperse helps astronomers understand the life cycle of matter in galaxies. The gas and dust in molecular clouds originated from earlier generations of stars that synthesized heavy elements in their cores and expelled them in stellar winds and supernova explosions. This enriched material then condensed into new molecular clouds where it forms new stars, some of which will also return material to the interstellar medium, continuing the cycle. The Orion region, with its ongoing star formation, represents one step in this cosmic recycling process, and studying it in detail helps us understand how galaxies convert gas into stars, and how the chemical composition of stars changes over successive generations as heavy elements accumulate. The hidden members. The constellation Orion, as recognized by the International Astronomical Union, includes not just the 7 bright stars that form the familiar pattern, but also hundreds of fainter stars that fall within the constellation's official boundaries. These boundaries, established in 1930 to create a systematic division of the celestial sphere into 88 non-overlapping regions, define Orion as an irregular polygon covering 594 square degrees. Within this region lie several thousand stars bright enough to be visible in amateur telescopes, and millions of stars detectable with professional observatory instruments. Most of these stars are much fainter than the 7 bright naked-eye stars, either because they are intrinsically less luminous or because they are much more distant, or both. Understanding the full population of stars in the Orion region requires surveys that detect and catalog faint stars, measure their properties, and determine which stars are physically associated with the Orion region and which are merely foreground or background objects that happen to lie in the same direction. One important class of stars in the Orion region is the young, low-mass stars still surrounded by the disks of gas and dust from which they formed. These objects, called T Tauri stars, after the first example discovered, are typically only a few million years old and have masses similar to or smaller than the Sunday. They are variable in brightness, often flaring unpredictably due to magnetic activity or the infall of material from their surrounding disks. T Tauri stars are much fainter than massive blue supergiants, so they are invisible to the naked eye, even though some lie closer to Earth than the bright constellation stars. However, telescopic surveys have identified thousands of T Tauri stars in the Orion region, particularly in and around the Orion Nebula, where star formation is currently most active. These young stars represent the bulk of the stellar population forming in Orion, since low-mass stars vastly outnumber high-mass stars in any star-forming region. For every massive blue supergiant like the belt stars, hundreds of sun-like stars form, and thousands of red dwarf stars, the smallest and faintest stars capable of sustaining nuclear fusion, also form. The Orion OB1 Association, the loose grouping of hot massive stars that includes the belt stars and several other prominent Orion members, actually contains hundreds of member stars when fainter members are included. Astronomers identify association members by looking for stars with common space motions, similar distances, similar ages, and similar chemical compositions, all indicating a shared origin in the same giant molecular cloud. The association is divided into 4 subgroups, labeled Orion OB1A, OB1B, OB1C, and OB1D, representing regions at slightly different distances and with slightly different ages, suggesting that star formation swept through the region in a wave from northwest to southeast over a period of about 10 million years. The OB1, a subgroup in the northwestern part of the constellation, is the oldest, with ages around 10 to 12 million years. The OB1b subgroup, which includes the belt stars Alnitak and Mintaka, has ages around 5 to 8 million years. The OB1c subgroup, which includes the Orion Nebula region, is the youngest with ages less than 1 million years. The OB1d subgroup lies south of the OB1c region and has intermediate ages. Understanding these subgroups and their ages helps astronomers reconstruct the history of star formation in the region and understand how stellar feedback from early generations triggered or influenced later generations. Many of the stars in the Orion region are too deeply embedded in dense molecular clouds to be seen at visible wavelengths, because dust grains absorb and scatter visible light very efficiently, making even relatively nearby objects invisible if enough dust lies between them and us. Infrared observations, which can penetrate dust much more effectively than visible light, reveal a hidden population of stars and protostars that would be completely unknown if we relied only on optical telescopes. The infrared astronomical satellite, launched in 1983, conducted the first complete infrared survey of the sky and discovered hundreds of previously unknown young stellar objects in Orion. Subsequent infrared missions, including the Spitzer Space Telescope and the Herschel Space Observatory, have provided even more detailed infrared views, revealing the internal structure of molecular clouds and identifying thousands of protostars in various stages of formation. Some of these objects are so young and so deeply embedded that they have not yet begun nuclear fusion and are shining only with the gravitational energy released as they contract, glowing primarily in the far infrared at wavelengths 10 to 100 times longer than visible light. Radio observations provide yet another window into the Orion region, detecting emission from molecules like carbon monoxide, ammonia, and formaldehyde that exist in the cold molecular clouds. Radio telescopes can map the distribution, temperature, density, and velocity of the gas in molecular clouds, revealing how the gas is moving and where it is being compressed by stellar feedback. These observations show that the Orion molecular cloud complex is not a static structure, but a dynamic, evolving system with gas flowing in complex patterns, some regions collapsing to form stars, other regions being dispersed by stellar winds and radiation, and shock waves from stellar winds and past supernovae, compressing gas and triggering new collapse. Combining observations at radio, infrared, visible, ultraviolet, and X-ray wavelengths provides a complete picture of the Orion region that no single wavelength could provide alone, revealing stars in all stages of formation and evolution, molecular clouds in all stages of collapse and dispersal, and the complex interactions between stars and gas that drive the ongoing evolution of this rich and active region of our galaxy. The life and death of Orion stars. The stars that make up the Orion constellation are not eternal but are born, live, and die according to the inexorable laws of physics that govern all stars. The massive blue supergiants that dominate the constellation are particularly short-lived, burning through their nuclear fuel at prodigious rates and facing violent ends as supernova explosions. Understanding the life cycle of these stars helps us appreciate not only how big Orion is in spatial extent, but also how fleeting the constellation is in temporal terms. The familiar pattern we see today will not exist forever, but will gradually change as stars evolve, explode, and fade away, ultimately leaving the constellation unrecognizable compared to its current appearance. In astronomical terms, the Orion constellation is a temporary arrangement of young, massive stars that have illuminated this region of the galaxy for only a few million years and will disappear within another few million to perhaps 20 million years. A mere eye blink in the multi-billion-year history of our galaxy. The most massive stars in Orion, including the belt stars Alnilam and Alnitak, and possibly Rigel, have masses 20 to 40 times the Sun's mass, and luminosities tens of thousands to hundreds of thousands of times the Sun's luminosity. These stars burn through their hydrogen fuel incredibly rapidly, exhausting their core hydrogen in only a few million years compared to the Sun's 10 billion-year main sequence lifetime. The luminosity of a star scales roughly as the fourth power of its mass, meaning a star with twice the Sun's mass is about 16 times more luminous, while a star with 10 times the Sun's mass is about 10,000 times more luminous. This extreme luminosity means massive stars radiate enormous amounts of energy per second, quickly converting their hydrogen fuel into helium through nuclear fusion. Once the core hydrogen is exhausted, the star's core contracts and heats until it becomes hot enough to fuse helium into carbon and oxygen, while hydrogen continues fusing in a shell surrounding the core. This shell burning causes the star to expand dramatically, transforming from a hot blue supergiant into a cooler red supergiant like Betelgeuse. Betelgeuse represents a later evolutionary stage than most of the other bright Orion stars, having already exhausted its core hydrogen and begun fusing heavier elements. The star is currently fusing helium in its core and hydrogen in a shell, but it will soon exhaust its core helium and begin fusing carbon, then neon, then oxygen, then silicon, creating an onion-like structure with shells of different elements burning at different depths. Each successive fusion stage produces less energy and lasts a shorter time. So while hydrogen burning lasts millions of years and helium burning lasts hundreds of thousands of years, carbon burning lasts only thousands of years. Oxygen burning lasts about a year, and silicon burning lasts only about 1 week. Eventually, the core becomes pure iron, which cannot be fused to release energy because iron is the most stable nucleus, and fusing it would require energy input rather than releasing energy. At this point, the star has no more nuclear fuel, and the core collapses catastrophically under its own gravity, compressing to densities comparable to atomic nuclei and rebounding in a shock wave that rips the star apart in a supernova explosion. When Betelgeuse explodes as a supernova, which could happen any time from tomorrow to 100,000 years from now, it will briefly shine as bright as the full moon, despite being 550 light-years away, and it will be visible in daylight for weeks or months, before gradually fading over a period of several months to years. The explosion will eject most of the star's mass into space at speeds of 10,000 to 20,000 kilometers per second, enriching the interstellar medium with heavy elements synthesized in the star's core and in the supernova explosion itself. The core will collapse into either a neutron star, an incredibly dense object about 20 kilometers in diameter with the mass of about 1.4 times the Sun, or possibly a black hole, if the core's mass exceeds about 3 solar masses. The supernova will be easily visible to anyone on Earth with clear skies, and it will be one of the most studied astronomical events in history, observed by professional and amateur astronomers worldwide, using instruments spanning the electromagnetic spectrum. However, the explosion will pose no danger to Earth because the distance of 550 light-years is far enough that the radiation and particles from the supernova will be dispersed and diluted to harmless levels by the time they reach us. The other massive blue stars in Orion will eventually suffer similar fates, exploding as supernovae over the next few million to 20 million years, depending on their exact masses and evolutionary states. Rigel, Saiph, and the belt stars Al-Nilam, Al-Nitak, and Mintaka are all massive enough to end as supernovae, and their explosions will briefly make each star shine with the combined luminosity of an entire galaxy of stars. If we could watch the Orion constellation over millions of years in fast forward, we would see the stars evolving, some expanding into red supergiants, some exploding in brilliant flashes of light, new stars forming in the molecular cloud to replace those that died, the constellation pattern gradually distorting as stars move through space at different velocities, and eventually the entire region dispersing and fading as star formation ceases and the remaining stars drift apart and dim. The constellation Orion as we know it is a snapshot of a particular moment in the evolution of this region, a moment that will pass as all moments do, leaving behind only neutron stars, black holes, and faint, low-mass stars that will continue shining for billions of years, but will be too faint to form prominent constellation patterns visible from Earth. The cultural legacy across time. The Orion constellation has held cultural significance for virtually every civilization that has looked up at the night sky, and its prominence in human culture reflects not just its visual distinctiveness, but also its visibility from most inhabited regions of Earth and its association with seasons and agricultural cycles. The constellation rises in the eastern sky in early evening during the northern hemisphere autumn, and dominates the winter sky, setting in the west in early evening by late spring. This seasonal visibility meant that ancient agricultural societies could use Orion's appearance or disappearance as a calendar marker for planting or harvesting crops, making the constellation practically important beyond its mythological significance. In the northern hemisphere, Orion's appearance in the evening sky coincided with the approach of winter, while in the southern hemisphere, visible as an upside-down pattern, Orion appeared prominently during summer months. This universal visibility from both hemispheres made Orion one of the few constellations recognized in some form by cultures in Europe, Asia, Africa, the Americas, and Oceania, though the patterns and stories associated with it varied widely. The ancient Sumerians, who lived in Mesopotamia about 5,000 years ago, recognized the constellation and associated it with their great hero Gilgamesh, a legendary king whose exploits were recorded in the Epic of Gilgamesh, one of the oldest known works of literature. The Sumerian constellation Gilgamesh appears to correspond roughly to the Greek Orion, though the exact identification remains uncertain due to incomplete preservation of Sumerian astronomical texts. The Babylonians, who succeeded the Sumerians in Mesopotamia, continued recognizing this constellation and called it the true shepherd of Anu, associating it with agricultural and pastoral themes. Babylonian astronomical texts contain detailed observations of stars and planets, tracking their positions and motions through constellations, including the true shepherd, and these observations contributed to the development of mathematical astronomy and the ability to predict planetary positions and eclipses. In ancient Egypt, as mentioned earlier, Orion was identified with Osiris and the constellation's heliacal rising, its first appearance in the pre-dawn sky, after a period of being behind the sun, coincided with the annual flooding of the Nile River that brought fertility to the land. The Egyptians aligned temples and monuments with Orion stars, including the famous alignment of the Giza pyramids with the belt stars, and they included representations of Orion in tomb paintings and religious texts as part of their complex mythology surrounding death, resurrection, and the afterlife. The star Sirius, the brightest star in the sky, which lies southeast of Orion in the constellation Canis Major, was associated with the goddess Isis, Osiris's wife, creating a celestial parallel to the mythological couple. The heliacal rising of Sirius occurred shortly after that of Orion and was such a significant event in the Egyptian calendar that it marked the beginning of the new year and the start of the annual flood season. This connection between sky and earth, between celestial patterns and terrestrial events, made astronomy central to Egyptian religion and culture. Indigenous peoples of the Americas developed their own constellation patterns and mythologies for the stars we call Orion, demonstrating that the human tendency to see patterns and create stories is universal, even though the specific patterns and stories vary. Many Native American tribes saw the three belt stars as representing different things, sometimes three hunters pursuing game, sometimes canoes or other objects important in tribal life. Some tribes recognized larger patterns in the region, including Orion and surrounding constellations, creating mythological narratives that explained creation, the cycle of seasons, and moral lessons about proper behavior. The Maya of Central America, who developed sophisticated mathematical astronomy and created complex calendars, incorporated Orion into their astronomical observations and associated it with the deity Hun-Hunappu, a god associated with maize and agricultural fertility. The Inca of South America recognized the belt stars and surrounding region as part of their extensive constellation system, which included both bright star patterns like Orion and dark cloud constellations formed by dark dust lanes in the Milky Way, a unique feature of Andean astronomy not commonly found in other traditions. In the Southern Hemisphere, Australian Aboriginal peoples, who maintained continuous cultural traditions for tens of thousands of years, making them among the oldest existing cultures on Earth, recognized patterns in the Orion region as part of complex Dreamtime stories that explained creation, law, and the relationships between people, land, and sky. Different Aboriginal groups had different constellation patterns and stories, reflecting the diversity of cultures across Australia, but many incorporated the belt stars and surrounding bright stars into patterns representing animals, people, or canoes, depending on the specific tradition. Aboriginal astronomy was practical as well as mythological, with celestial observations used to predict seasonal changes, animal behavior, and the availability of food resources, demonstrating sophisticated understanding of the connections between sky and earth. The Maori of New Zealand similarly incorporated Orion into their navigation and seasonal calendars, and Polynesian navigators used Orion along with other constellations to navigate across thousands of miles of open ocean, maintaining accurate courses to distant islands using only the stars, sun, ocean swells, and their deep knowledge of natural patterns. The modern scientific exploration. The scientific study of Orion transformed dramatically in the 20th century with the development of new technologies, including photography, spectroscopy, radio astronomy, infrared astronomy, and eventually, space-based observatories that could observe wavelengths blocked by Earth's atmosphere. These tools allowed astronomers to move beyond simple naked-eye observations and distance measurements to detailed physical studies of the stars, nebulae, and molecular clouds in the region, revealing Orion as a complex, dynamic system rather than a static pattern of stars. Early photographic surveys in the late 19th and early 20th centuries revealed the extent of the nebulosity in the Sword region and discovered fainter nebulae and star clusters that had been invisible to naked eye. Observers' long-exposure photographs showed that much of the Orion region is filled with faint, glowing gas and dark dust clouds, creating intricate patterns of light and shadow that earlier observers had missed. These photographs inspired artistic as well as scientific interest, with the beautiful colors and structures of the Orion Nebula appearing in paintings, poetry, and popular writings that brought astronomical imagery to broader public audiences. Spectroscopic studies of Orion's stars revealed their chemical compositions, temperatures, surface gravities, and motions, allowing astronomers to classify the stars and understand their physical properties. Spectroscopy involves splitting starlight into its component colors and analyzing the pattern of dark absorption lines and bright emission lines that appear in the spectrum. Each chemical element produces a unique pattern of lines at specific wavelengths determined by the quantum mechanical energy levels of electrons in atoms of that element. So identifying which lines appear in a spectrum reveals which elements are present in the star's atmosphere. Spectroscopy also reveals temperature through the intensity distribution across different wavelengths and surface gravity through the width of spectral lines, which broaden when gas density and pressure are high. By the mid-20th century, astronomers had obtained detailed spectra of all the major Orion stars and used these spectra to determine that the blue stars are extremely hot, with temperatures 20,000 to 30,000 degrees Celsius, while Betelgeuse is much cooler at about 3,500 degrees, and that all these stars contain similar relative abundances of chemical elements, with hydrogen and helium dominating, and heavier elements like carbon, nitrogen, oxygen, and iron present in small amounts. The discovery of the cosmic radio background and the development of radio astronomy in the 1940s and 50s opened an entirely new window on the Orion region, revealing emission from molecular gas that was invisible at optical wavelengths. Radio telescopes detected emission from molecules like carbon monoxide, ammonia, formaldehyde, and many others, showing that the dark regions between stars are not empty, but filled with cold molecular gas and dust. Mapping this molecular emission revealed the full extent of the Orion molecular cloud complex and showed where the gas is dense enough to be collapsing to form new stars. Radio observations also detected emission from ionized hydrogen gas in the Orion Nebula, providing complementary information to optical observations and revealing the structure of the ionized region carved out by the hot trapezium stars. These observations demonstrated that star formation is an ongoing process, with molecular gas collapsing to form new stars that then ionize the surrounding gas and create the glowing nebulae we see at optical wavelengths. Infrared observations, which began from high-altitude aircraft and balloons in the 1960s and 70s and expanded dramatically with dedicated infrared space telescopes starting in the 1980s, revealed yet another hidden aspect of Orion, a large population of young stars still embedded in dense cocoons of dust. The infrared astronomical satellite discovered hundreds of infrared sources in Orion that had no optical counterparts, indicating stars too young and too deeply buried in dust to be visible at optical wavelengths. The Spitzer Space Telescope and the Herschel Space Observatory provided even more detailed infrared views in the early 21st century, imaging the internal structure of molecular clouds and revealing protostars in the earliest stages of formation, some still accreting material from their surrounding disks, some surrounded by jets and outflows of gas ejected along the star's rotation axis. These infrared observations showed that the star formation we see in the visible Orion Nebula is only the tip of the iceberg, with far more extensive star formation occurring in the dark molecular clouds that surround and permeate the entire region. X-ray observations from space-based X-ray telescopes, including Einstein Observatory, ROSAT, Chandra, and XMM Newton, revealed that young stars in Orion are powerful X-ray sources, emitting high-energy radiation from their hot coronae and from magnetic flares similar to, but much more powerful than, solar flares. These X-ray observations provided crucial information about the magnetic activity of young stars and the interactions between young stars and their surrounding protoplanetary disks. The Chandra X-ray Observatory has obtained extremely detailed images of the Orion Nebula region, showing thousands of X-ray emitting young stars, revealing that X-ray emission is ubiquitous among young stars regardless of their mass, from massive hot stars down to brown dwarfs, objects too low in mass to sustain hydrogen fusion and therefore intermediate between stars and planets. Understanding this X-ray emission helps astronomers comprehend how magnetic fields and high-energy radiation affect planet formation in protoplanetary disks, potentially influencing whether Earth-like planets can form and whether they can retain atmospheres. The Orion Nebula as a cosmic laboratory. The Orion Nebula deserves special attention as perhaps the single most studied object in the night sky beyond our solar system, observed by every major telescope and space observatory since the invention of the telescope. The nebula is close enough and bright enough that even small amateur telescopes reveal its structure, making it accessible to millions of people worldwide, while its richness and complexity reward observation with the most powerful professional instruments. The nebula's importance for astronomy cannot be overstated. It is the nearest region of massive star formation to Earth, the only such region close enough that we can study individual forming stars in detail rather than seeing star-forming regions as unresolved blurs of light. The Orion Nebula serves as a template for understanding how massive stars form throughout our galaxy and throughout the universe, and studying it has generated fundamental insights into stellar birth, the physics of ionized gas, the structure of protoplanetary disks, and the interactions between young stars and their environment. The Orion Nebula is classified as an HII region, a volume of space where hydrogen gas is ionized by ultraviolet radiation from hot young stars. The term HII refers to ionized hydrogen atoms that have lost their electrons, as opposed to HI, which denotes neutral hydrogen atoms, and H2, which denotes molecular hydrogen. The intense ultraviolet radiation from the trapezium stars, particularly Theta 1 Orionis C, with its surface temperature of about 40,000 degrees, is energetic enough to ionize hydrogen atoms, stripping electrons from the nuclei. When these electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, including the famous hydrogen alpha line at 656.3 nanometers in the red part of the spectrum, giving the nebula its characteristic pinkish-red color in photographs. Oxygen also becomes ionized and emits green light at 507 nanometers when doubly ionized oxygen recombines with electrons, and nitrogen emits red light at similar wavelengths to hydrogen. These emission lines are what make the nebula glow, and by analyzing the strengths of different emission lines, astronomers can determine the temperature, density, and chemical composition of the glowing gas. The structure of the Orion Nebula is complex, with filaments, sheets, and clumps of gas at different densities and temperatures. The brightest part of the nebula, easily visible in amateur telescopes, is only the surface of a much larger molecular cloud, the part that has been ionized and heated by the trapezium stars. Behind this glowing surface lies the dense, cold molecular cloud from which the stars formed and in which star formation continues. The boundary between the ionized nebula and the neutral molecular cloud is called a photodissociation region, or PDR, a narrow layer where ultraviolet radiation is strong enough to dissociate molecules and heat the gas, but not strong enough to ionize it completely. PDRs are important for understanding the chemistry of interstellar gas because many molecules are destroyed in PDRs, while others are created, and understanding PDR chemistry helps astronomers interpret observations of star-forming regions throughout the galaxy where similar physical conditions exist. One of the most exciting discoveries in the Orion Nebula came in the 1990s, when observations with the Hubble Space Telescope revealed structures called proplyds, short for protoplanetary disks, around many of the young stars in the nebula. These are disks of gas and dust surrounding young stars, the raw material from which planets will form, similar to the protoplanetary disk that surrounded the young Sun 4.6 billion years ago, and from which Earth and the other planets formed. The Hubble images showed proplyds as tadpole-shaped structures with a bright central star and a dark disk viewed edge-on, with a tail of material streaming away from the disk, blown away by the intense radiation from the nearby trapezium stars. These proplyds are being photo-evaporated, meaning the ultraviolet radiation heats the outer layers of the disk and gives molecules enough energy to escape, gradually dispersing the disk over timescales of hundreds of thousands to millions of years. This photoevaporation limits the time available for planet formation, suggesting that planets must form relatively quickly before the disk is destroyed, a constraint that informs theoretical models of planet formation. The Orion Nebula has also been crucial for understanding stellar winds and outflows from young stars. Many young stars in the nebula drive powerful jets and bipolar outflows, beams of gas ejected along the star's rotation axis at speeds of hundreds of kilometers per second. These outflows collide with the surrounding molecular cloud, creating shock waves that heat the gas and cause it to emit light in specific emission lines. By observing these outflows and shocks, astronomers learn about the magnetic fields and rotation of young stars, the interaction between the star and its surrounding disk, and the processes by which angular momentum is removed from the star disk system to allow material to fall onto the growing star. Outflows from young stars also inject energy and momentum into molecular clouds, creating turbulent motions that can both support clouds against gravitational collapse and also create dense regions that collapse to form new stars, illustrating the complex feedback loops that regulate star formation. The future of Orion. The constellation Orion, as we see it today, is a temporary arrangement, and on timescales of millions of years, the pattern will change dramatically as stars move through space, evolve, and explode. Understanding the future evolution of Orion requires combining knowledge of stellar evolution, stellar motion through space, and the ongoing dynamics of star formation and feedback in the region. The massive blue stars that currently dominate the constellation are all doomed to short lives ending in supernova explosions, and once they explode and fade, the constellation will look very different. Betelgeuse will likely be the first of the major constellation stars to explode, possibly within the next 100,000 years, though it could survive for another million years depending on its current evolutionary state and internal structure. When it explodes, it will briefly shine as one of the brightest objects in the sky before fading away over several months to years, leaving behind a neutron star or black hole invisible to the naked eye and removing one of the constellation's most distinctive features, the bright orange shoulder star. Over the next few million years, the other massive stars in Orion will also explode, one by one, with the order depending on their exact masses and evolutionary states. Rigel, the brightest star in the constellation, might explode within a few million years, as might Saiph and the belt stars Alnilam, Alnitak, and Mintaka. Each supernova will briefly create a brilliant new star in Orion, brighter than any planet, visible in daylight, casting shadows at night, before fading away and disappearing from view. If we could watch Orion over millions of years in time-lapse, we would see these stars wink out one by one, like candles being extinguished, leaving behind only the fainter stars that were always there but overshadowed by their more brilliant companions. Bellatrix, the remaining bright star, is also massive enough to eventually explode, but is younger and less evolved than Betelgeuse and the others, so it will probably survive for tens of millions of years, long after the current generation of supergiants has vanished. Eventually, Bellatrix too will explode, and at that point, none of the current 7 bright stars of Orion will remain visible. Even before the stars explode and disappear, their motions through space will gradually distort the constellation pattern. All stars are moving through the galaxy with individual velocities determined by the circumstances of their birth and subsequent gravitational interactions with other stars and molecular clouds. These space velocities typically range from tens to hundreds of kilometers per second, seeming slow by cosmic standards, but fast enough to produce noticeable changes in constellation patterns over tens of thousands of years. The stars of Orion have different space velocities because they are not all gravitationally bound to each other, and over time, their different motions will cause them to drift apart, stretching and distorting the familiar pattern. Computer simulations that project the future positions of Orion's stars based on their measured velocities show that in 50,000 years, the constellation will still be recognizable but noticeably distorted, with the belt stars no longer perfectly aligned and the quadrilateral formed by the corner stars noticeably skewed. In 100,000 years, the pattern will be significantly altered, and in 500,000 years, it will be unrecognizable, bearing no resemblance to the constellation we see today. Star formation in the Orion region will also change over the next few million years as the molecular cloud is consumed by star formation and dispersed by stellar feedback. Currently, the Orion molecular cloud complex contains enough material to form thousands more stars, and star formation is proceeding vigorously in several locations, including the Orion Nebula. However, the intense ultraviolet radiation and stellar winds from massive stars already formed are heating and compressing the remaining molecular gas, and the supernova explosions of these stars will inject enormous amounts of energy into the cloud, potentially dispersing much of the gas and halting star formation. Theoretical models suggest that the Orion molecular cloud complex will be largely dispersed within about 10 million years, with some gas falling back and possibly forming a second generation of stars after a period of quiescence, while other gas is expelled from the region entirely and dispersed into the general interstellar medium. This cycle of star formation, feedback, dispersal, and eventual regathering of material is typical of star-forming regions throughout galaxies and represents one step in the galactic scale recycling of matter between stars and the interstellar medium. Far in the future, billions of years from now, long after the current Orion constellation has completely disappeared and been forgotten, the Sun itself will evolve off the main sequence and enter its red giant phase, expanding to enormous size and swallowing the inner planets, including Earth. By that time, the stars that currently make up Orion will be long gone, the massive ones having exploded as supernovae billions of years earlier, the lower mass ones having evolved into white dwarfs, or still shining as red dwarfs depending on their masses. The region of space we now call Orion will contain a completely different population of stars, many not yet born at the present time, forming new and different patterns that future observers, if any exist, will name and mythologize according to their own cultures and imaginations. The constellation patterns we see today, including Orion, are transient features, snapshots of particular arrangements of stars at a particular moment in cosmic time, meaningful to us because we live at this moment, but having no lasting significance in the vast spans of time over which the universe evolves. Orion in human space exploration. As humanity begins to explore space beyond Earth's orbit and contemplate eventual interstellar travel, the Orion constellation takes on new significance as a destination rather than merely a pattern to observe. The nearest star in the Orion constellation, Betelgeuse at 243 light-years, is far beyond the reach of current spacecraft technology, but it is not inconceivably distant for future technologies that might be developed over coming centuries. Light takes 243 years to travel from Betelgeuse to Earth, meaning any spacecraft traveling at 1% the speed of light, an extraordinarily ambitious goal with our current understanding of physics, would take 24,300 years to reach Betelgeuse. Even traveling at 10% light speed, pushing the boundaries of imaginable propulsion technologies, the journey would take over 2,000 years, far longer than human civilization has existed in its current form. Nevertheless, these distances are finite rather than infinite, and there is nothing in our current understanding of physics that absolutely forbids travel across such distances given sufficient time, energy, and technological sophistication. The challenges of interstellar travel are immense and go far beyond simple speed and distance. A spacecraft traveling at a significant fraction of light speed would encounter enormous kinetic energy hazards from interstellar dust and gas, with even tiny particles delivering devastating impacts due to the extreme relative velocity. Shielding against such impacts would require massive amounts of material, potentially making the spacecraft too heavy to accelerate to high speeds. Energy requirements are equally daunting, with current propulsion technologies utterly inadequate for accelerating even small masses to appreciable fractions of light speed. Various theoretical propulsion systems have been proposed, including fusion rockets, antimatter drives, light sails pushed by powerful lasers, and even more exotic concepts like generation ships that would take centuries to reach their destinations and would need to support human populations across multiple generations. None of these technologies currently exist in practical form, and many would require advances in physics, materials, science, and engineering far beyond our current capabilities. Despite these challenges, the Orion constellation represents a tangible set of destinations for interstellar exploration, helping to make the abstract concept of space travel concrete and motivating research into the technologies that would be required. NASA's Orion spacecraft, designed for missions to the Moon and eventually Mars, was named after the constellation, drawing symbolic connection between humanity's first steps beyond low Earth orbit and our ultimate destiny among the stars. Various science fiction works have used Orion stars as destinations for interstellar voyages, and the constellation appears frequently in speculative discussions about where humanity might travel if and when interstellar capability is achieved. The stars of Orion are young, massive, and luminous, making them attractive destinations for scientific exploration to study stellar evolution, massive star formation, and exotic phenomena like supernovae, though the same youth and instability that make them scientifically interesting also make them potentially hazardous for human exploration. One particularly intriguing aspect of Orion for future exploration is the Orion Nebula and its associated star-forming regions. These regions contain thousands of young stars, many surrounded by protoplanetary disks where planets are forming, offering an opportunity to study planet formation as it happens, rather than attempting to reconstruct the process from observations of mature planetary systems. If humanity ever achieves the capability for interstellar travel, the Orion Nebula region would be a prime scientific target, allowing direct observation and study of stellar birth and planetary system formation. The region might also contain planets around young stars, potentially offering locations for scientific outposts or even eventual colonization, though the intense radiation environment around young massive stars would pose severe challenges. Any planets in the Orion Nebula region would be very young, no more than a few million years old, and would likely be inhospitable with no evolved biospheres, but they might still offer resources and scientific value, justifying the immense effort of interstellar travel. The timescales of human exploration and the timescales of stellar evolution in Orion present an interesting intersection. If humanity develops interstellar travel capability within the next few hundred to few thousand years, the Orion constellation will still exist in essentially its current form, with all the major stars still shining and the overall pattern still recognizable. However, if interstellar travel takes tens or hundreds of thousands of years to achieve, the constellation will already be significantly altered by stellar evolution and proper motion, and if it takes millions of years, the constellation will have completely disappeared. This creates a kind of cosmic window of opportunity where the Orion we know exists for us to explore if we can develop the necessary technologies quickly enough, but will be gone if we delay too long. This perspective adds poignancy to the constellation, reminding us that the patterns we see and the opportunities they represent are not permanent, but fleeting on cosmic timescales, existing only for a moment in the vast expanse of astronomical time. The scale in perspective. To truly grasp how big the Orion constellation really is, we must place it in context by comparing it to other structures in the universe at different scales, from the familiar sizes of everyday objects through planetary and stellar scales up to galactic and cosmological scales. This journey across scales reveals where Orion fits in the hierarchy of cosmic structures and helps us comprehend distances and sizes that are otherwise too vast for human intuition to grasp. Starting at human scales, the distance across a typical room is about 10 meters. The distance from New York to Los Angeles is about 4,000 kilometers. Earth's diameter is about 12,700 kilometers, large enough that you could fit 300 Earths side by side across the diameter of the Sunday. The distance from Earth to the Sun is about 150 million kilometers, or 1 astronomical unit, the fundamental unit for measuring distances within our solar system. The solar system extends about 40 astronomical units to Neptune's orbit and perhaps 100,000 astronomical units to the outer edge of the Oort cloud, the distant reservoir of comets. Beyond the solar system, distances become so large that even astronomical units are inadequate, and we must use light years or parsecs. The nearest star to the Sun, Proxima Centauri, lies about 4.2 light-years away, or about 266,000 astronomical units, roughly 30 trillion kilometers. This is the distance light travels in 4.2 years, moving at 300,000 kilometers per second. The Orion constellation, with its nearest major star Bellatrix at 243 light-years and its farthest major star Alnilam at 2,400 light-years, spans a range of distances, roughly 600 times the distance to Proxima Centauri. The depth of space containing the major Orion stars is about 2,200 light-years, meaning light takes 22 centuries to cross from the nearest major constellation star to the farthest. To put this in perspective, light that left Alnilam 2,400 years ago, around the time of ancient Greece and the Persian Empire, is just arriving at Earth now, while light that left Bellatrix 243 years ago, around the time of the American Revolution, is arriving now. The Orion constellation, vast as it is, occupies only a tiny portion of our Milky Way galaxy. The Milky Way is a spiral galaxy, about 100,000 light-years in diameter, and perhaps 10,000 light-years thick in the main disk, though exact measurements are difficult because we are embedded within it. The Orion region lies in the Orion Arm, a minor spiral arm or spur connecting two major spiral arms, located about 26,000 light-years from the galactic center and several thousand light-years from the nearest major spiral arm. In galactic terms, Orion is a local neighborhood, a small region within a larger structure spanning 100,000 light-years. The galaxy contains between 100 billion and 400 billion stars, with uncertainty arising from difficulty counting faint stars and from not knowing how many stars exist in the galaxy's outer regions. The brightest stars in Orion, despite their tremendous luminosities, are invisible beyond a few thousand light-years. So the stars we see forming the constellation pattern are all relatively nearby members of our galactic arm. Beyond our galaxy lie other galaxies scattered through the observable universe. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away, roughly 1,000 times the depth of the Orion constellation. Andromeda is a spiral galaxy somewhat larger than the Milky Way, and it is the most distant object easily visible to the naked eye, appearing as a faint, fuzzy patch in the constellation of the same name. Light from Andromeda takes 2.5 million years to reach us, meaning we see Andromeda as it appeared 2.5 million years ago, long before humans evolved. The observable universe extends roughly 46 billion light-years in all directions, limited not by the size of the universe itself, which may be infinite, but by the finite age of the universe. About 13.8 billion years, and the finite speed of light. Light from the most distant observable objects has been traveling toward us since shortly after the Big Bang, and we can never see farther than the distance light has traveled since the universe began. In this cosmic scale, the Orion constellation is a tiny local structure, a neighborhood within our galaxy, smaller than our galaxy by a factor of 50, and smaller than the observable universe by a factor of 20 million. Yet to us, Orion is vast and incomprehensible, spanning distances we cannot directly visualize or emotionally grasp. This paradox of scale, where something simultaneously tiny and huge depending on the reference frame, characterizes much of astronomy and reminds us that human intuition evolved to handle sizes and distances relevant to survival on Earth's surface, not to comprehend the cosmos. The Orion constellation is neither large nor small in any absolute sense, but occupies its particular place in the hierarchy of structures, large compared to solar systems and stellar neighborhoods, small compared to galaxies and the universe, exactly the size it is because of the particular distribution of stars that happen to lie in that direction from Earth, and the particular moment in cosmic time when we observe them, the methods of measurement. Understanding how astronomers measure the distances, sizes, and properties of objects in the Orion constellation reveals the ingenuity and persistence required to study things we can never directly touch or visit. Every measurement in astronomy is indirect, relying on observations of light combined with physical laws and mathematical relationships to infer properties that cannot be measured directly. The most fundamental measurement is distance, because almost everything else we want to know about a celestial object depends on knowing how far away it is. A star's luminosity can only be calculated if we know its distance and apparent brightness. Its size can only be calculated if we know its distance and angular size, or if we know its luminosity and temperature. Without accurate distances, our understanding of the universe would be severely limited. So the development of reliable distance measurement techniques has been one of astronomy's highest priorities for centuries. The most direct method of measuring stellar distances is trigonometric parallax, which we have discussed earlier. This method relies on observing how a star's apparent position shifts when viewed from opposite sides of Earth's orbit, 6 months apart. The parallax angle, measured in arcseconds, is inversely proportional to distance, with larger angles indicating nearer stars and smaller angles indicating farther stars. A star at a distance of 1 parsec would show a parallax of 1 arcsecond, where 1 parsec equals 3.26 light-years. Bellatrix, the nearest major Orion star at 243 light-years, has a parallax of about 13 thousandths of an arcsecond, while Alnilam, at 2400 light-years, has a parallax of only about 1,000th of an arcsecond. Measuring such tiny angles requires extraordinary precision, achieved through careful observation, statistical averaging of multiple measurements, and elimination of systematic errors from instrumental and atmospheric effects. The Gaia satellite, which measures parallaxes from space, achieves precision better than 20 millionths of an arcsecond for bright stars, allowing reliable distance measurements out to several thousand light-years. For stars beyond the range of reliable parallax measurements, astronomers use a ladder of distance indicators, where each method is calibrated using closer objects with known distances and then applied to more distant objects. One important rung in this distance ladder is the use of spectroscopic parallax, which, despite its name, does not actually measure parallax, but rather estimates distance from a star's intrinsic luminosity. By analyzing a star's spectrum to determine its temperature, surface gravity, and chemical composition, astronomers classify the star and estimate how luminous it should be based on the properties of similar stars with known distances. Comparing this estimated intrinsic luminosity to the star's observed apparent brightness allows calculation of distance using the inverse square law. This method works well for stars of well-understood types, but has significant uncertainties for unusual stars or for stars whose spectral classification is ambiguous. For the massive hot stars in Orion, spectroscopic parallax was the primary distance measurement method before space-based parallax measurements became available, and it gave reasonably accurate results because hot, massive stars have well-understood spectral properties. Another distance measurement technique uses variable stars whose intrinsic brightness varies periodically in ways that correlate with their average luminosity. Cepheid variable stars, which pulsate with periods ranging from days to months, show a tight relationship between pulsation period and average luminosity, with longer period cepheids being more luminous. By measuring a cepheid's pulsation period and apparent brightness, astronomers can calculate its distance. This technique is crucial for measuring distances to nearby galaxies and forms an important rung in the cosmic distance ladder, though cepheids are relatively rare and none exist among the main stars of the Orion constellation. Another class of variable stars, RR Lyrae stars, serve a similar function for measuring distances to star clusters and to the galactic halo. These distance measurement techniques, combined with observations of stellar motion through space using Doppler spectroscopy, build a comprehensive, three-dimensional picture of stellar positions and velocities throughout our region of the galaxy. The measurement of stellar properties beyond distance and brightness requires additional techniques. A star's temperature can be determined from its color or from detailed analysis of its spectrum, with hotter stars appearing bluer and showing spectral features characteristic of highly ionized elements, while cooler stars appear redder and show molecular absorption bands. A star's radius can be calculated from its luminosity and temperature using the Stefan-Boltzmann law, or for very nearby large stars like Betelgeuse, it can be measured directly using interferometry, a technique that combines light from multiple telescopes to achieve the resolution of a much larger telescope. A star's mass, the most fundamental property determining everything else about it, can be measured directly only for stars in binary systems, where orbital motion reveals the gravitational forces between components. For isolated stars, mass must be estimated from theoretical models or from empirical relationships between mass and other observable properties like luminosity and temperature. These various measurement techniques, each with its own limitations and uncertainties, combine to give us a comprehensive understanding of the stars in Orion and throughout the galaxy. The Orion in different wavelengths. The familiar view of Orion that we see with our eyes represents only a tiny fraction of the information available from the constellation if we observe it across the full electromagnetic spectrum, from radio waves to gamma rays. Each wavelength range reveals different physical phenomena and different populations of objects, and combining observations at multiple wavelengths creates a complete picture impossible to obtain from optical observations alone. At radio wavelengths, spanning from millimeters to meters, radio telescopes detect emission from cold molecular gas in the Orion molecular cloud complex, from ionized gas in HII regions like the Orion Nebula, and from energetic electrons spiraling in magnetic fields around young stars. Radio observations reveal the full extent of the molecular cloud and show where gas is dense enough to be forming stars, complementing optical observations that see only the surfaces of clouds where dust does not block the view. At infrared wavelengths, spanning from about 1 micron to 100 microns, or roughly 1 to 100 times the wavelength of visible light, infrared telescopes detect thermal emission from cool objects including dust, grains, protostars still embedded in cocoons of dust, and the cool surfaces of red giant stars like Betelgeuse. Infrared light penetrates dust much better than visible light, allowing infrared telescopes to peer into dense molecular clouds and detect protostars that would be completely invisible at optical wavelengths. The Orion region is bright in the infrared, particularly in the Orion Nebula, where thousands of young stars glow with the heat of their formation, and surrounding protoplanetary disks emit infrared radiation from dust grains warmed by the central stars. Infrared observations have revealed far more young stars in Orion than optical observations, showing that the visible Orion Nebula is only a small part of a much larger star-forming complex hidden by dust. At optical wavelengths, the wavelengths visible to human eyes, spanning from about 400 to 700 nanometers, telescopes see the photospheres of stars, the emission from ionized gas in nebulae, and the scattered light from dust grains illuminated by nearby stars. The familiar constellation pattern is an optical wavelength phenomenon created by the combined light of stars whose peak emission happens to fall in or near the optical range. The blue stars of Orion are actually brightest in the ultraviolet, but enough ultraviolet light spills over into the blue end of the visible spectrum that these stars appear brilliant blue-white to our eyes. Betelgeuse peaks in the near-infrared but emits enough orange and red light to be easily visible and distinctively colored compared to the blue stars. Optical observations have revealed the detailed structure of the Orion Nebula, showing filaments, sheets, bubbles, and knots of glowing gas shaped by stellar winds and ionization fronts. At ultraviolet wavelengths, spanning from about 10 to 400 nanometers, telescopes observe the hottest stars and the most energetic phenomena. The massive blue stars of Orion emit most of their energy in the ultraviolet, and this ultraviolet radiation is responsible for ionizing the hydrogen gas in the Orion Nebula, making it glow at optical wavelengths. Ultraviolet observations reveal the intense radiation fields around young massive stars and show how this radiation affects surrounding gas and dust. Earth's atmosphere blocks most ultraviolet light, so ultraviolet astronomy requires observations from space using satellites like the Hubble Space Telescope and dedicated UV missions. These observations have revealed that the space around young stars is filled with far more energetic radiation than optical observations alone would suggest, with important implications for planet formation and the survival of protoplanetary disks. At X-ray wavelengths, spanning from about 0.1 to 10 nanometers, X-ray telescopes detect the hottest gas in the universe, with temperatures of millions of degrees. Young stars in the Orion region are strong X-ray sources because their surfaces are covered with hotspots created by magnetic activity, and they produce frequent flares that heat gas to X-ray emitting temperatures. The Chandra X-ray Observatory has obtained spectacular X-ray images of the Orion Nebula, showing thousands of individual X-ray sources, most of them young stars, less than a few million years old. These X-ray observations reveal the magnetic activity of young stars and the hot gas created when stellar winds collide with surrounding material. At gamma-ray wavelengths, the highest energy form of light, telescopes detect the most energetic phenomena, including supernova explosions and the acceleration of particles to nearly light speed. The current stars of Orion have not yet exploded as supernovae, so gamma-ray observations do not yet show dramatic emission from the constellation. But when the massive stars do explode, they will briefly shine brightly in gamma rays. The question of life. One of the most profound questions we can ask about the Orion constellation is whether life exists anywhere in the vast volume of space it encompasses. With thousands of stars in the Orion region, many of them young and presumably surrounded by planetary systems in various stages of formation, the statistical likelihood that at least some planets exist in potentially habitable conditions seems high, yet the specific circumstances required for life to emerge and survive may be rare enough that life is absent despite the abundance of stars and planets. Understanding the potential for life in Orion requires considering what conditions are necessary for life, how common these conditions might be around the types of stars found in Orion, and whether the intense radiation environment and stellar activity in star-forming regions helps or hinders the emergence of life. These questions touch on the emerging field of astrobiology and the search for life beyond Earth, one of the most exciting frontiers in contemporary science. The massive blue stars that form the visible constellation pattern, including the belt stars, Rigel, and the others, are almost certainly not hosts for life on planets around them because their lifetimes are too short and their radiation too intense. These stars live only a few million to perhaps 20 million years before exploding as supernovae, far too short for life as we know it to emerge and evolve to complexity. On Earth, life began roughly 3.8 billion years ago, shortly after the planet's surface cooled enough to support liquid water. But complex multicellular life did not emerge until about 600 million years ago, and intelligent life, capable of technology, emerged only within the last few 100,000 years. If similar timescales apply elsewhere in the universe, then billions of years are required for complex life to develop, far longer than massive stars survive. Additionally, the intense ultraviolet radiation from hot blue stars would damage biological molecules and strip away planetary atmospheres, making the habitable zones around such stars inhospitable for life, despite the abundance of energy available. The lower mass stars in the Orion region, including the thousands of Sun-like and red dwarf stars currently forming in the molecular cloud, are much more promising candidates for hosting life. These stars will live for billions of years, providing ample time for life to emerge and evolve. Many of these stars are surrounded by protoplanetary disks visible in Hubble Space Telescope images of the Orion Nebula, and planet formation is presumably underway in at least some of these disks. However, the environment in a dense, star-forming region like Orion is dramatically different from the relatively isolated region where our Sun formed. The intense ultraviolet radiation from nearby massive stars photoevaporates protoplanetary disks, potentially destroying them before planets can fully form, or at least reducing the amount of material available for planet formation. Observations suggest that disks in the Orion Nebula are being eroded at rates that would completely disperse them within a few million years, possibly too quickly for Jupiter-sized planets to form, though Earth-sized rocky planets might form faster and survive. Even if planets do form and survive in the Orion region, the question of whether life could emerge on them depends on many factors, including the availability of liquid water, the presence of organic molecules, the stability of planetary climates over long timescales, and the frequency and intensity of catastrophic events like asteroid impacts or nearby supernova explosions. The eventual supernova explosions of the massive stars in Orion will bathe the entire region in high-energy radiation and accelerated particles, potentially sterilizing any planets within a few tens of light-years of each explosion. A supernova, within 10 light-years, would deliver enough radiation to severely damage Earth's ozone layer and cause mass extinction, and a supernova within 100 light-years would deliver detectable but probably not catastrophic doses of radiation. Many of the young stars in the Orion Nebula lie within 10 to 20 light-years of massive stars that will eventually explode, suggesting that these systems might be repeatedly sterilized by supernovae, preventing the long-term survival of complex life, even if it does emerge. Despite these challenges, the sheer number of stars in the Orion region, perhaps 10,000 to 100,000 stars depending on how we define the region's boundaries, suggests that at least some planets might harbor life, or at least conditions favorable for life. The detection of life or biosignatures on planets in the Orion region is currently beyond our technological capabilities because even the nearest Orion stars are too distant for detailed spectroscopic analysis of planetary atmospheres. Using current telescopes, future missions, including extremely large ground-based telescopes and advanced space observatories, might have the sensitivity to detect biosignature gases like oxygen, methane, or other molecules produced by life in the atmospheres of planets around the nearest Orion stars, particularly Betelgeuse at 243 light-years. Such detections would be extraordinarily difficult and require years of observations to confirm, but they are not impossible, and if life is common in the galaxy, the Orion region's abundance of young stars makes it a reasonable place to search. The cosmic perspective. After this long journey through the Orion constellation, exploring its stars, nebulae, molecular clouds, and place in the cosmos, we can finally answer the question posed at the beginning. How big is the Orion constellation really? The answer is complex and multifaceted, depending on what aspect of size we consider and what scale we use for comparison. In terms of angular size on the sky, Orion covers about 594 square degrees, roughly 1.4% of the celestial sphere, making it a moderately large constellation visible across a substantial portion of the night sky. In terms of the distances to its stars, Orion spans from about 243 light-years for Betelgeuse to about 2,400 light-years for Alnilam, a depth of 2,200 light-years or roughly 13 quadrillion miles. In terms of the volume of space encompassing its major stars, Orion occupies roughly 10 million cubic light-years, a vast region that nevertheless represents only a tiny fraction of our galaxy's volume and an infinitesimal fraction of the observable universe. But perhaps the most important measure of Orion's size is not physical, but conceptual. Orion is big enough that understanding it requires grasping distances and scales far beyond human everyday experience, forcing us to develop new mathematical and conceptual tools to comprehend what we observe. Orion is big enough that light takes centuries to millennia to cross from one side to the other, meaning the constellation we see is not a snapshot of a single moment, but a collage of different times, with light from different stars having left on its journey to Earth during different historical epochs, from recent centuries to ancient millennia. Orion is big enough to contain thousands of stars, vast clouds of gas and dust, with masses equivalent to hundreds of thousands of suns, regions where new stars and planetary systems are forming, and massive unstable stars approaching violent ends as supernovae. The constellation is big enough to have been recognized and named by every major civilization in human history, prominent enough to appear in the mythology and cultural traditions of peoples separated by continents and millennia, united only by their shared view of the same sky. The story of Orion is ultimately the story of humanity's expanding comprehension of the universe. For thousands of years, people saw Orion as a pattern on the celestial sphere, a mythological figure close enough to reach up and touch, if only we could climb high enough. The measurement of stellar parallax in the 19th century revealed that the constellation stars were not equally distant but scattered through space at different depths, destroying the illusion of the celestial sphere and revealing the three-dimensional nature of the cosmos. The development of spectroscopy and astrophysics in the 20th century revealed the physical nature of stars as balls of plasma powered by nuclear fusion, each with its own temperature, mass, luminosity, and evolutionary history. The discovery of molecular clouds and star-forming regions showed that space between stars is not empty, but filled with the raw material of future stars and planetary systems, and that stars are not eternal, but are born, live, and die according to physical laws we can understand and quantify. The development of space-based telescopes operating at wavelengths from radio to gamma rays revealed hidden populations of young stars, protoplanetary disks, magnetic fields, and energetic phenomena invisible to human eyes, but crucial for understanding how the region works. Each advance in our understanding has made Orion simultaneously more mysterious and more comprehensible, revealing new questions even as old questions were answered. We now know the distances to Orion's stars with unprecedented precision, yet we still debate exactly how old these stars are and exactly when they will explode. We can image protoplanetary disks around young stars in the Orion Nebula, yet we do not fully understand how planets form or how common Earth-like planets are in such environments. We can measure the properties of the Orion molecular cloud and track the ongoing star formation, yet we cannot predict in detail which regions will form stars next or how stellar feedback will affect the remaining cloud. These open questions drive ongoing research and motivate new observations with ever more sophisticated instruments, continuing the process of discovery that has characterized astronomy since its beginning. The Orion constellation also serves as a reminder of our place in the universe, simultaneously insignificant and central. Insignificant because the constellation is a local structure in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies, vast as it seems to us, yet tiny in cosmic terms. The matter and energy in Orion represent a negligible fraction of the total matter and energy in the universe, and the constellation's existence or non-existence makes no difference to the universe at large. Yet Orion is central to our human experience because we are here, now, able to observe it and contemplate it. The constellation has guided travelers, inspired artists, organized agricultural calendars, and appeared in the stories and spiritual traditions of countless cultures. It has driven scientific inquiry and technological development as we built ever better instruments to study it. It has expanded our understanding of the cosmos and our conception of our place within it. In this sense, Orion is as big as the meaning we find in it, as large as the questions it raises and the wonder it inspires. As we look to the future, the Orion constellation will continue to evolve and change on timescales ranging from years to millions of years. New stars will form in the molecular cloud, adding faint new members to the stellar population. The massive blue stars will explode as supernovae, temporarily creating brilliant new lights in the night sky, before fading away and leaving behind invisible remnants. The constellation pattern will gradually distort and eventually disappear as stellar motions carry the stars to different parts of the sky. Future generations of humans, if we survive and prosper, will see different constellations and create different myths, though perhaps they will remember the stories their ancestors told about the hunter who once strode across the winter sky. The Orion we know exists for this moment in cosmic history, visible to us because we happen to live at the right time and the right place to see this particular arrangement of stars. This temporal limitation adds poignancy to our observations, reminding us that we are privileged to witness something that past observers could not see, having not yet been born, and that future observers will not see, having missed the window of time when this pattern existed. The question of how big Orion really is ultimately has no single answer, because size is not a simple property, but depends on perspective, measurement method, and what aspect of size we consider. Orion is as big as the distances between its stars, measured in light years spanning from hundreds to thousands. It is as big as the volume of space it occupies, measured in millions of cubic light years. It is as big as the molecular cloud that connects its stars, measured in hundreds of light years across and hundreds of thousands of solar masses. It is as big as its influence on human culture and scientific understanding, immeasurable in physical units, but profound in its impact on how we see ourselves and our world. Orion is exactly as big as it needs to be Orion, no more and no less. A collection of stars and gas and dust arranged by chance and viewed from our particular location in space and time, creating a pattern that has captivated humanity for millennia and will continue to inspire wonder and curiosity for as long as humans look up at the night sky and ask questions about what they see. This is how big Orion really is. Big enough to make us feel small, big enough to inspire us to reach beyond our limitations, big enough to remind us that the universe is vast and ancient and beautiful beyond our ability to fully comprehend, yet knowable through patience, observation, and reason.